What I'm going to talk about in this talk is something a little bit more technically specific than just architecture in general, but rather now go into some patterns and stuff, specifically within event-driven architecture. I've got a lot of really cool patterns to show you. However, it's probably worthwhile to spend about 5 minutes talking about what event-driven architecture really is. Just so we have that little refresher, because there's some terminology that I'm going to be using that's kind of important to know. But event-driven architecture is not new. It's been around for probably about 3 decades now. So it seems like it's new, but it's really not. But it is an architecture style that leverages asynchronous processing to be able to trigger events and to respond to those events. Now, when we look at kind of an event-driven architecture here, and what we have, because I know these are small, and I did, right before Neil finished, was able to upload these slides. So, so they are actually on my website. So you can go to the downloads/gids2023.html to get these. But let me explain what we've got going on here. We've got a bunch of services. Now, these services formally are called event processors in EDA, event-driven architecture. But in today's world, we usually call them services. So here you can see I've got an order placement. I'll do these ones over here. A payment, and then a fulfillment service to fulfill the order. Inventory and warehousing over here. Notification to notify the customer that the order is on the way. And then shipping right over here. So kind of all the basic kinds of services to order something online, pay for it, and have it shipped to you. Okay, but we're going to use event-driven architecture. So what you see in this particular architecture here are a bunch of components I'm going to show you. And the first of those happens to be what's called an initiating event. Now, this is the event. Notice it's in turquoise because we're going to be revisiting this whole thing to show the patterns. But the initiating event is the event that actually kicks off an entire process. For example, I want to purchase a book. That's the initiating event. So then what we have are something called formally processing events. But in today's world, these are usually called derived events. These are events that are going to be triggered based on the action of placing this order. And different services will then trigger these, for example, but also services will then respond to these events. Okay. So it kind of is really as simple as that. This is not complex. We have events, we trigger them, we respond to them, highly decoupled. Well, if that were only true, because it is quite complex. Yes, what I showed you were a bunch of happy paths of a few events. What happens if all of a sudden we have a lot of events, error handling, and all these questions come up? Well, wait a minute. Before you continue, Mark, is there actually a difference between a message and an event? Because we use the same term. Is that okay? Also, how much data should I include in the event payload? I showed you that in my keynote. That's another question. How can I guarantee that I don't lose an event? We're using event-driven architecture, and these are important messages. Is there ever a chance I might lose one? But also, how can I increase the overall concurrency of events and still maintain the processing order of events? This is all about event timing. Event A has to happen before event B, for example. How do I partition event brokers to get better reliability in my system? Should I have 1 broker, 2, 3? Where should they go? And also, how do I determine the state of that flow? Where is my order? Has it been paid? I'm curious to know where it is. So all of these pieces. Oh, and finally, how can I increase the capacity and throughput? We've done an acquisition, and all of a sudden now we have twice as many events, and we can't process them fast enough. How do you do that? This is what makes event-driven architecture hard. You see, I showed you it's just a bunch of events, an initiating event, and some services. Just stitch them together and it's fine. These are only a few. of the dozens of challenges we have in event-driven architecture. So in this session, I can't cover all these questions, but I'll cover most of them by showing you some patterns of event-driven architecture. Now, what I want to start with, though, is to show you, is there a difference really between an event and a message? Is there a difference between an event-driven system and a message-driven system? Because we have microservices, and we're using messages. Is that event-driven microservices? So that's the first thing we'll actually discuss. Then I'll show you something called the event forwarding pattern. This pattern will guarantee 100% that you will not lose an event. I'll show you how that pattern works as well. We'll look at something called the domain broker pattern. This is about more the physical topology of how many queues or how many brokers should I have? Do I have one Kafka cluster or maybe 6? Can you help me answer that? Sure, there's a pattern for that. It's called the domain broker pattern. We'll take a look at some workflow state patterns. As a matter of fact, I'll show you 2 different ones for managing state. And I'll show you one that's very common, and I'll show you why it doesn't work well. So I'm going to show you 2 patterns to how to determine how to know the state of events happening in the system. And then finally, I'll take a look at something to speed up the processing of our eventing system, and that's the multi-broker pattern. Okay, so these are the core 5 I'm going to show. I believe I have time for these. But if I hurry, I'll show you a couple of others. Okay. All right. Well, let's start with kind of the most basic question. Oh, by the way, Neil just mentioned in the last talk, there's this thing called trade-offs in architecture. Guess what? There's trade-offs in patterns as well. And so for every one of these patterns, I'm going to actually show you all the good things about them, because they solve a lot of problems. But I'm also going to show you all of the bad things about them, the trade-offs, because you may not want to apply all of these patterns. All of them have some consequences that we should be aware of when using these. Okay, so let's actually start simply. I'm going to be showing, unfortunately, not a lot of demos because I only do have 50 minutes left. But I do have 2 GitHub repos where you can actually go to see a lot of these patterns and more actually implemented. And it's on my GitHub repo, which is WMR513. And in there specifically, what I'll be showing are patterns for event-driven patterns, and also some of these are under reactive as well. So you can take a look at some of the source code for some of the things I'll be showing you. Okay. All right. Events versus messages. Any difference? Yes. There are differences. There's 4 main differences I want to show you. So therefore, these terms really are not interchangeable. And let me show you. So we've got here an order, what is that? Oh, that's an order placement and payment. Order placement and payment. So I'm ordering something, I need to pay for it. Event-driven says this. An event is something that I am advertising to the system. I just did something. For example, I just placed an order. I'm advertising something that is a state change that I did that happened in the past. That's an event. Versus a queue, or I say not a queue, but a message which says, I would like you to do something for me. It's more of a command or a query. I just received an order, and I'm going to hand it over to Hugo, and I'm going to say, can you please pay for this? I need to send him something. That's a big difference, you see, because when I say, hey, everybody, I'm a service, I'm order placement, I just placed an order. Here you go. And I hand out the event. It's up there somewhere. I'm done. And I can walk off stage. Because I have no idea who will receive that event, respond to that event, and react to that event. I have no idea. That's an event. But a message I need Hugo to pagar, pay. I need dude to pay. So the point is, I'm trying to learn Spanish, so there we go. That was my little attempt. So I have to direct that message specifically to Hugo, not anybody else. Okay, so that's the first key difference. The other is about ownership. You see, with event-driven, it turns out that the sender owns that event channel, owns that queue or topic. That's mine. So I know where it is. All of you have to go and search for it and say, oh yeah, that's Mark's topic right there. But you know what's interesting? This is exactly backwards in messaging. In messaging, Hugo owns the queue, not me. So I have to go and find, where's Hugo? Oh, there he is, right there. You're going to be speaking next, right? Yes, exactly. So there we go. I have to know where to go find him. Okay. You all have to know where to go find me. That's the difference. Now, there's also a difference with the contract. Because you see, with events, I am telling all of you, I just placed an order. I own that contract. I own the schema of that contract, what information I'm going to send you. But in messaging, it's completely backwards. Hugo owns the contract. I have to conform to his. There's one other subtle difference. With events, it's generally publish and subscribe, notification services, streams, these sort of things. It's broadcast. Whereas with messaging, this is typically point-to-point. Queues, SQS, for example, queuing services. These would be kind of things like direct exchanges, these sort of things within queuing. Okay, so those are the differences. So in fact, yes, there is a difference between these terms. And it's fairly important to understand which one you're doing. So they're not interchangeable. All right, let's start taking a look at patterns now. The first and simplest, I was almost about to say, I'm going to skip this one because it's so basic. But I realized just because it's basic and simple doesn't mean it's not important. So this might be a review for some of you, but for others, it's like, yeah, we have dropped messages all the time. We have dropped events, and it's a big problem for us. Well, let me show you a pattern on how to fix that. Because it turns out that it is very, very easy to simulate messages or events getting lost in a system. So this is really asking the question, how do I guarantee that no messages or events will ever be lost when passing them from one service to another to another? Well, let me show you the problem that occurs first. If I have service A way on the left-hand side, and I have an event, the first place I could actually lose data is getting that to the channel, to the queue or the topic. Because maybe it got there, didn't send me an acknowledgement, and I crashed. So there's a chance of actually losing data. Also, maybe it got there and the broker crashed. Data's gone. Now, the most common way of losing data is when I receive that event or message and I respond to it. This is the most common because that event is no longer on that queue or topic. I'm processing it and I crash. Oh, data's gone. It's off the queue. It's completely gone. The third place is that now that I, as service B, have the data, I'm trying to get it to its final place, the database. And some error happens in between there, either with the database or me, and I crash. So it's three places. So basically, every time that event goes from one place to another, I have a chance of losing that. Well, let's apply something called the event forwarding pattern. Also, it's not called, but sometimes based on the chain of persistence pattern. And so what this does is follows. Let's take a look at the first one here. So when I have service A to get to the queue, how can I guarantee I will never lose an event? Two techniques. The first is to use something called synchronous send or publish. and persisted messages. If that message is persisted, the queue can come down, it can come back up, no problem. It's persisted in some sort of file or database. I'm not reliant on that broker anymore. Now, it usually stores it in memory as well, but if it crashes, it'll just bring it back up. Okay. Synchronous send is necessary because most languages, most frameworks will allow you to do something called async send. As a matter of fact, in the Java platform, this was introduced about 10 years ago, I guess, in JMS 2. And the idea here is that I don't have to wait for the acknowledgement of the broker because persisted messages are slow. They're really slow. And so the point is, I've got a lot of work to do. So how can I speed it up? Promises, futures. So I'm going to send an event, persisted, but I'm going to go and do other things. La, 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 la. Okay, I'm kind of done. I'm going to wait for that future. There it is. I got the acknowledgement. Okay, now I can complete. If you care about your messages or events, don't do that. Because in between that time, I send it to the broker and start walking around here on stage, I can crash. And I never got the acknowledgement from the broker that it ever received it. So that will get rid of all the flames there. Now, what about the most common? When I receive something from the queue, it disappears. This is actually fairly straightforward. So in regular messaging, I can use something called client acknowledge mode. Client acknowledge mode, which is the default, by the way, in SQS, basically says, hey, give me the next message, but don't remove it from the queue. Just mark it with my client ID so that everybody knows I'm processing it. Don't retrieve that. The brokers do that all for you. So client acknowledge mode or basic default in SQS, well, if I crash, the data's still on the queue. Somebody else will pick it up. If I'm no longer there, the client ID gets removed, and one of you starts picking that up and processing it. Can't lose data. It's in the queue. I haven't acknowledged I have processed it yet. Then, that third one is when it gets to the database. Here, I can use something called last participant support, LPS. Now, what this means is not a framework, it's a technique. You can try to do two-phase commit, but that's still not a guarantee. So here's what I do. It's in the database. I get a commit, but notice it's also in the queue. The very next line of code says message.acknowledge. And when I do that, it then removes it from the queue, and it's in its final resting place. It's like a chain of persistence. For SQS, I basically execute a delete. And so instead of that acknowledge, SQS would be delete. And then it deletes the message. Huh. Well, wait a minute. Yeah, this is great. This is an awesome pattern. Why wouldn't I ever use it? Because here, there's no message loss. I mean, okay. We could have this really horrible discussion. Well, what if the database or the file system goes down? Well, then just use rack or something. I mean, we can have those things, but that's all operational that we can harden. But my point is we have high data integrity. Trade-off? Yeah, well, performance and throughput. This will be about 3 to 4 times slower than if you were to use non-persisted messages. That's the difference in speed. Yeah. I could process about 12,000 events per second on any standard broker. Persisted, 3 to 4,000, max. So that's a trade-off. Also, the other problem is I've now, where I didn't have the problem before, have just now introduced duplicates. You see, let's pretend Hugo here is the queue. Okay, so the message is on the queue here in the front with Hugo. All right, so I go to process it, and all of a sudden, I go to do the update. I do the commit, and before I have a chance to acknowledge the message, it's only 2 lines of code, but before I have the chance to do that, boom, I crash. Where's the data? It's in the database. Where's the data? Hugo still has it. I crashed. What are the other of you? Go ask Hugo and say, oh, well, there's another message. It's free now. And all of a sudden, you try to do the insert. Boom, duplicate. Yeah, so we have to handle that as well through here. So those are the consequences of this particular pattern. Okay, like I said, it's the most basic kind of pattern, but it is important to know these kind of techniques and the trade-offs. Which is more important, high data integrity or sheer raw performance? Pick one. Now, for you Kafka users and stuff, there's another cautionary tale here because Kafka gets its sheer raw throughput through batching. Me? I may spend 20, 30, 40 messages before they actually get transmitted to Kafka. They're in memory. So the safe way to do that is to set the batch size to 1. So every send to Kafka, stop, let me connect, let me make sure Kafka has it, get the acknowledgement, and come back. Oh, is that slow? So we have the same trade-off. Kafka does not answer this question. We have the same trade-off here. Any of these optimizations that leverage in memory, we have the opportunity to miss or lose messages. Okay, let's look at another pattern that doesn't really relate to code, but really about architecture. And that's the domain broker pattern. So how do I partition and manage my brokers for maximum reliability in my system? We need a highly reliable system, and we don't have highly reliable brokers. Okay, how can I solve this problem? So isn't it interesting? Here's our architecture we've been looking at here, where we have all of our services and the derived events. Where's the broker here? You're going to find this piece amazing. Where's the broker? Well, it's right there. We have one broker. We've got all these topics and queues, or one service which has all of these. Yeah, there it is. Whoops. Hold on. I need to go backwards. Just one here. Went a little far. There we go. Okay. We have one broker. Huh. Never thought of that. But it's clustered, so we're not concerned. Or are we? You see, do you remember I talked about the ownership? In event-driven architecture, the owner is me. I need to publish that event for all of you. What does that mean? That means I, the order placement, am dependent on that broker. If that broker fails, I can't accept your order. I'm sorry, I'm going to pass back an error to the client. Order placed. Are you dependent on that topic for processing? No, you're not. Oh, you need it, but you're not going to crash. You're just going to process other events or something. I don't know, I can't get to that broker. That's fine. I can still do other things, but I can't. Why? Because I own it. And what does that mean? It is the writer of the message that owns it, because I am dependent on that broker. So let me go backwards one. Look at all the dependencies. They're in red. All those little red lines, those dotted lines, are all writes. What do you suppose if that broker goes down or becomes unavailable or crashes or just simply stops? It happens. My entire system just went down because no one can write to those queues or topics or streams. Okay, so how do we fix this problem? Well, we do what's called federating the broker, because what we're looking at here is something called an architectural quantum. Now, this was introduced way back in the building let me say that again. This was produced way back in the Building Evolutionary Architectures book that Neil Ford wrote. We refined it in the Architecture of the Hard Parts. It's even further refined in the second edition of Building Evolutionary Architecture. So what does that mean, that architectural quantum? Well, let me show you the definition, because this becomes vitally important. You'll see it in several patterns here. So this is an independently deployable artifact with high functional cohesion and synchronous dynamic coupling. I have no idea, Mark, what you're talking about. Okay, fine, I got the definition. I'm going to ignore it because I don't understand it. And isn't that funny? How many times if we see something and we don't understand it, what do? Just ignore it. Well, it doesn't matter then, but it does. Okay, so let's actually use an example to actually understand why this concept is so important and critical. What I'm talking about is a portion of the system that can stand alone from all other parts of the system. That's what I mean about a deployable artifact, an independent deployable artifact. It's not a single service. It's all the parts needed for high functional cohesion. The user interface is required. The gateway is required. The service is required. And the database is required. If any one of those 4 parts is not available, I can't process. I'm dependent on those. That's what I mean. It's all 4 of those. Maybe it's also, you've got a load balancer. That would be included in it as well. So here's an architecture right here. This one, although you can't read, does electronics recycling. I want to recycle my electronic device instead of throw it in the trash. Okay, well, I can get money for it. Oh, now you've got me interested. I mean, being environmentally safe is one thing, but being able to make money from it is another. So, yes, I would like to recycle my device. Well, look at the services we have here. I broke up the user interface, so we've got a kiosk recycling the device, a public UI, all those things, all sharing the same database. So we look at how many pieces of this system do we have? And the answer, everybody, is 1. There's just one single architectural quantum here. This is caching. Yeah, caching. Boy, oh boy. There we go. Why? Because if I lose the database, I lose all functionality. That's what the synchronous dynamic coupling is. Let's do a better example. We have 3 parts of the system right here. Part A, Part B, and Part C. So we've got 3 parts. Okay. These are all independent of each other, but I'm the database. And you're all dependent on me. We're all one unit. Even though we're distributed, we're all just one unit. And it turns out that all the architectural characteristics we've been talking about exist at the quantum level. So how do we break this apart? Well, if you're dependent on the database here, I'd have to break apart the database, wouldn't I? We have our own database. This part has its own database. And over here. Fantastic. But the problem is, let's do this. Okay. So here we go. So gentlemen in blue, right? And in red. Can you guys shake hands? I know you don't like each other, but can you shake hands? Okay, now hold on there. Everybody look. That's a synchronous binding. The 2 of them are synchronous, like a REST call. Okay. What does that mean? They're dependent on each other. Okay, that's good. Thank you. Oh, that's fantastic. But do you see, if we all just started shaking hands synchronously or holding hands because like, you know, I need you here. Don't leave. I'm nervous. I'm dependent on you. Then it doesn't matter that we've broken apart the database. That's the synchronous coupling part. So, if we did async, boom, 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 now we're all 3 parts again. And that's the idea of a driver for breaking apart a database, breaking apart a user interface, breaking apart a gateway. Look at this diagram here if you can. I broke apart the database, I've broken apart the user interface, so micro front ends. Now, that is a separate architectural quantum. It's an independently deployable part of my system. That could go and be moved all the way over to the other side of the stage. This is still bound to the database, synchronously. Okay, you'll see why this matters greatly now. Okay, so that's a quantum. Multiple quantum are called a quanta. Okay, why does this matter? Boy, that was a weird tangent. Why? Wait. He was talking about brokers and queues. This is why it matters. How many architectural quanta exist in my highly distributed event-driven architecture here? 1. Exactly. Well, no. Each service has its own UI, its own database. Yeah. What is it all bound to? The broker. No, but it's highly available and clustered. It's still a single architectural quantum, which means that's where all of the characteristics live, no matter if they need them or not. So how can we make this more effective? And the answer? Break it apart. Try to find domains. And this is why the name domain broker pattern. What are our basic domains here? Let's see. Let's do this one. Okay, so the first one here would be order placement and payment. You know, those two are both sort of coupled because those both need to happen in terms of placing an order. I'm going to make that a domain. I'm going to make that a broker. And now, that's a separate architectural quantum, a separate piece of the system. Still bound together, but a separate piece. I look over here and I find that warehousing and inventory are kind of related. We'll make that a domain. I'm going to give them their own broker. Notice they both write to it, as do order placement and payment, both write to those queues at that broker. Okay, now, what about order fulfillment? Oh, wait, what about order fulfillment? It needs to read or respond to that event over here. Why is that not part of that architectural quantum? Because it's not dependent on it. That broker goes down, order fulfillment is still running and just fine. It's just not processing anything. So you see, it's a big difference whether you're reading or writing to either a database or a queue or any of these. Right now we're doing async. So I've got that one there. Order fulfillment and shipping. These are kind of related. I'm going to create a domain there, add a broker. And finally, notification. Well, it sends out a notification event that I just sent something to a customer. There we go. So notice if you're writing it, it has to be within that quantum. Now, what do you think about my reliability of the system? It's pretty good. Because now, if the order placement quantum, if that broker goes down, all the rest of these can still function just fine. Think about this. I can still do inventory and warehousing. I can still do order fulfillment and shipping. I'm no longer dependent on that. But you need to read from it. Sure, yeah. When it comes back up, read the events. Yeah. That's known as the broker domain pattern. It gives us guidance to know how many brokers, where they should be, and who should own them. I now have 4 separate parts of this system. It's a pretty cool pattern. Well, you're going to see it in action again. Okay. Well, wait a minute. That's pretty cool. As a matter of fact, just because I came to GIDS and attended this talk, you just actually solved one of our problems. So what's so bad about this? Because it preserves the quantum. We have separate parts of the system. Part 3, Part 2, and Part 1. These are all independent. If you guys crash, these two are still functioning just fine. Perfectly fine, because there's no dependencies here. That's what we want in a distributed architecture. Oh, and we get better reliability. Trade-offs are hard, aren't they? Ponder this for a second. Why wouldn't you do this? Huh. It's there, but I have no idea what it is. Anybody have it? Yeah. Thank you. Yeah. Complexity. Yeah. It's additional cost and additional complexity. Yeah, but that's not bad. Maybe not. That might not be very significant. But it's still a trade-off. You see, it's still there. Additional cost will always be a trade-off. Additional complexity will always be a trade-off here. Which is more important? Are we trying to save money? Because if we don't have the money, I mean, I would like a new fancy car. I mean, what's a trade-off of having a Ferrari? I can't afford it. Okay, there's a trade-off, actually, of having a nice red Ferrari. So yeah, it's additional cost and complexity. Thank you. Fantastic. Yeah. So if we don't need this kind of domain partitioning, then don't spend the money and complexity on it. Yeah. So that's the trade-off here. So, interesting question. How do you determine where in that order flow we are? Because event-driven architecture is highly decoupled. And as we saw yesterday, for those of you who attended my talk, I don't remember which one, we saw that the workflow is distributed everywhere. No one really knows what's going on. So how do I know? Turns out that there's two patterns we can actually look at. And so the first one, basically, is, where's my order? I'm sorry, sir, we have no idea. Oh, let me guess. You're using event-driven architecture. How did you know? Because I'm an architect. All right, so how can we fix this? Two different patterns, two different approaches. But I want to show you these patterns. But before I do, this is common to both. I don't have to care about every state in this whole flow. There are probably 100 derived events bouncing around through this entire system. So the first step in state management is saying which actions or events are important for this workflow. Order placed, is that important? Well, yeah, I need to know that the order's placed. The same thing that the payment is applied. This one here, that the order's been fulfilled, that the order's been shipped. Yeah, these are all part of the major workflow. Does the customer journey care that inventory was updated? Does the customer journey care that we've replenished our stock? Or that you notified me? I already know that, I got the email. No, these are internal events about internal state. This helps us a lot. Because a lot of times, we make the assumption that every event, every action has to be tracked in the workflow. Well, it doesn't. Okay, so that's the first step. What's important to us in the workflow that we want to track? Okay, let me show you two patterns. The first is really called a push-based state pattern. This is one of the most common patterns. Push-based means this. I need to know the state. Who should own the state? Well, I don't know. Maybe a new service. Maybe it should be the initiating service. The initiating event came into order placement. It kind of started the process. It should probably know where we're at. Plus, generally, those are the ones that are customer-facing. So I'm going to make that the state owner. Now, how does order placement know where we are in the system? I don't know. All of you are going to have to tell me. So what do I do? So the first thing I do is I create a queue. Now, this queue is owned by me, because this is going to be messaging within event-driven architecture. And you see, all the services that are involved with those major events all send me a state change. They all connect to the queue to send me a state change. It's all asynchronous. It's pretty fast. And then I listen for those state change events. And I update my database. There we go. Okay. So all of those state change events, order placed, go ahead, it sends it there, and I've got it. That is pretty cool. Or not. Because what's the implication here? Each service needs to trigger an event, but each service is now responsible for telling me what its state is. So we have a highly distributed workflow state. But the point is, payment knows payment is applied. It doesn't know about anything else, so it sends that to me. Okay, what could possibly go wrong here? It's pretty common. Oh, nice. Yeah. Who owns the queue? Yeah, the queue is owned by the order processing right here. Who needs to write to it? Everybody. What broker is that queue in? Mine. Oh, whoops. What have I just done? How many architectural quanta do I have now? 1. Wait a minute. Hold on. Mark. In the last pattern, you told us to federate the broker. You all have a broker. You have a broker. You have a broker. This is awesome. And now all of a sudden, order processing is right over there. All of you have to talk over there. What does that mean? You're writing to the queue. All of you are writing to the queue. And what have we done? Those 2 months of work and cost and complexity and expense to federate the broker didn't matter, because we're back to a single architectural quantum. Yeah. You see how easy it is to mess up systems. You know, we try so hard to apply all these patterns and everything's fine, and somebody says, hey, we need state management. Oh, just add a queue, push-based pattern. Yeah, it's fine. And we don't even see what we're doing. That's why this concept is so important. Always pay attention to the fact that are we now synchronously coupled to something else, somewhere else? That synchronicity, that requirement that you be there, man, that's like just, you know what it's like? It's taking a knife and going, blah, 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 to your system, right in its heart. Blah, blah. It's like, why are you doing this to me? I don't know, because it's hard. That's exactly what it is. This is a simple, honest mistake. Now just coupled your entire system together. Well, but this is how we do state management. Well, let me show you another approach. Okay, so the problem with push-based is this. First of all, it does give us a great separation of concern. The reason this is common is because we've separated the state management from all the processing. And that's a good thing. The initiating event now owns that. It's close to where it started. That's a good thing. But the problem, everybody, is it destroys the quantum. We have now coupled every broker together. Also, do you remember what the services have to do? They have to send me the state. This is additional service complexity. Every service, don't forget to do that. Oh, yeah, don't worry, I'll do it. Now, don't forget, you have to send me the state. No, that's fine, I got it. And you forget. Oh, boy. But also, the state machine is all distributed. Each service knows about it. So let's take a look at another pattern. This is a pull-based pattern. So you could, there's variants here, where you could still assign order placement as the owner. You could still do that. But let me show you another approach. And that's to create a separate service. Because now it can be context-based. And that's a state tracker. It owns the state. Mark, you could stop right here. Why? You're going to have the same problem. Nah, Mark always wins. Watch. I will figure out this problem. Watch this. I can still preserve all of the architectural quanta. Why? Watch this. Because you know what that state tracker does? It simply listens to existing events, just like everybody else. I am listening. Therefore, I'm not dependent. I listen for the order placed event. Now I can change the state. I listen for when the payment's applied. Now I can change the state. I listen when the order shipped or fulfilled and also shipped. Now I can update the state. So do you see where is the broker in this state management? Where it belongs in each domain. I'm just listening. No one's pushing it to me. I'm pulling it from all of you. Look at how simple this actually is. As a matter of fact, it's got a couple of great benefits. First of all, where is my state machine? And when I say state machine, I'm talking about all of the transition states, the before state, the after state, what that action might be, the before state, after state, a finite state machine. It's in one place, the state tracker, not distributed across all of you. That's convenient when we have to change the workflow, because now I change it in one place, the state tracker. I preserve the quantum. I've got, no service involvement. The services don't even know that state's being managed. Notice how simple I made the services now. Yeah, this is amazing when you start comparing patterns and you really see the differences between those. Well, wait a minute. So this is pretty good. Okay, trade-offs are hard, because I just don't know what to do here with this. Well, here's the thing. Usually we do have a separate state owner. You can mitigate that by adding complexity to changing it to the owner or the initiating event owner. But it's also implicit state management. In other words, I'm implying it just by reading the same events you are. Okay. All right, one more pattern I want to show you, and that's called the multi-broker pattern. So this asks the question, well, we just merged, or we just acquired a company, or we just released some new software and everybody's using us now. We can't process events fast enough. How can I increase the overall throughput and capacity of events through my system? Use Kafka. Okay, that's the end of the talk. No. Thank you, but I can't use Kafka. How can we simulate this kind of same thing when we can't use some of the tools and products that do help us with throughput? Because I just have a simple broker, okay? And I've got 3 services that all send events. And also I've got services that now respond to that event. Well, that single broker, everybody, this is non-persisted, can process a maximum of about 11,000 messages a second. That's a lot. However, here's the problem. Each client is producing 4,000 messages a second. That's the maximum. It doesn't matter if you add another queue. That's the max in the broker. So what happens? We're going to have a deficit of 1,000 messages a second. We can't keep up. This is simple math, folks. And this happens. We don't realize the scalability because, oh yeah, we got plenty of capacity. And all of a sudden, now we don't. So what do we do to fix this? Because that broker will go down. Okay, so by the way, all of those go down too. How do you fix this problem? Go back to a monolith. Yeah. Actually, I do a lot of teaching as well. I do public and private training courses. And I was at a particular training course, and it was on architecture, the hard parts. And it's hard. It's a 2-day class of a lot of the stuff you've been seeing here, but it's in a lot of detail with exercises. Everybody creates an architecture, this sort of thing. And we were towards the end of the class, and this was in London, and all of a sudden, it's the hardest exercise to kind of build everything together. And I had each team, I was calling on each team to say, okay, what did you guys come up with? What did you come up with? What did you come up with? And I got to the last team, and I said, okay, the team in the back, what's your solution to this particular problem? And they said, oh, it's right here. And they held up the paper, and it showed a modular monolith. It was just hilarious. I couldn't help but laugh, but that was their solution. They said, this stuff is just too hard. Okay. So how can we fix this problem? Again, we federate the broker within each domain. So the point is, within a domain itself, here's what I do. I have multiple brokers. I have consumer groups still listening on those. And now I use a simple round-robin algorithm because collectively, those 2 brokers, these would be 2 different instances or clusters of brokers. I'm not just clustering, I'm having 2 separate ones. Now, what's my capacity here? 22,000 messages a second. If I added a 3rd broker, I'd have 33,000 messages a second. And what do? Well, I just simply, every service does a simple round robin. I'm going to send to you, I'm going to send to you, I'm going to send to you. The other service, I'm going to send to you and you and you, you and you and you. I keep doing this. I've just increased the capacity of my system to 33,000 messages a second if all of you were separate brokers. This is all within that same domain. Isn't that cool? So we saw this kind of partitioning where we took our central broker, right here, me, and said, yeah, let's break it up into three sets. So we've got three domains. All three of these IL things are each domain. So we're going to have your own broker, your own broker, your own broker. But now, over here, this is all of our customer-facing stuff. We've got a lot of events. We can't keep up. Now, we're going to take me and replicate me just within here. That's what we're talking about here. All right. So really cool pattern, actually. So each of these just kind of start round-robining. And exactly, you know what's interesting? The multi-broker pattern, where have you seen this before? I'll give you a hint. It's a product that happens to be an author. Kafka. Yeah, this is the underlying concepts behind Kafka and how it works so fast. Each topic is separated into partitions. Clients are writing to a partition, not a topic. Yeah, same kind of principle we can apply in regular messaging, even services, even Kafka. If Kafka's too slow because we have too big of a message, create another instance of it and round robin to each of these two. Wow, this could just be endless. This is pretty cool. So, Kafka, I know you can process 2 million messages a second. So can we. It's pretty cool, isn't it? I keep bashing Kafka. I like Kafka. I use it a lot. Okay, so the benefit here is increased throughput, performance, scalability, capacity. Yeah, this is a great pattern. The negative? Yeah, not only cost and complexity, but unfortunately, because I'm talking to two different brokers, I lose FIFO order. Oh, we need that. Now there's another problem. Yeah, every pattern, whether it's a design pattern, an architecture pattern, it doesn't matter. Every pattern has a consequence. Look for it, because we were almost there. But yeah, we can't get rid of FIFO order. Now we have to use Kafka. All right, so those are a few of the many different patterns in event-driven architecture that really do help us solve some of these really hard problems. It's not as easy as just saying, oh, send an event, receive an event. No, there's a lot of stuff that can go on here. So anyways, thank you all so much.